Hi guys, welcome back to the channel. In this video I will cover the optical isomerism topic of the A-level chemistry curriculum. Let's get started. So there are two types of isomerism, one being structural and the other being stereoisomerism, and we have covered the chain isomerism, position isomerism, and the functional group from the structural isomerism, as well as covering the EZ isomerism from the stereoisomerism. So these were covered in my old video, which the link should be popping up now. So make sure you are aware of these before we're moving on to optical isomerism. Alright, so the optical isomerism just branches off the stereoisomerism, so it's one of the stereoisomerisms. So the definition of optical isomerism is that it has the same structural formulae, so the two molecules which will exhibit the optical isomerism will have the same structural formula, but the atoms will be arranged in different spatial arrangements. So when we talk about spatial arrangement, what we mean is the 3D shape of the molecule. So the 3D shape of the molecule will be different, but they will have the same structural formulae. So this type of isomerism occurs when the carbon, or it can be any molecule, but we only really look at carbon in A levels, but it's when any molecule is bonded to 4 different atoms or groups. So it has to be 4 different atoms or groups, 4 exactly. So if it was a trigonal planar, if it was only 3 different atoms or groups, then it won't be possible. If it was 5, it won't be possible, and it has to be 4 different ones. So if it was 3 and 2 different, 2 same, then this won't occur. So it has to be 4 different atoms or groups. And when this type of isomerism occurs, we say that the center molecule, so in most cases it's carbon, we say that it's a chiral or asymmetrical center, or chiral or asymmetrical carbon. So for example, in this picture, we have this carbon in the middle, which is bonded to 4 different atoms. So it has bromine, chlorine, hydrogen, and fluorine. So we can say that this is a chiral center, or we can say that this is a chiral carbon. If this had, instead of having chlorine, if this had hydrogen, then this would not be a chiral center, as it would be bonded to 2 same groups. So remembering that it's a tetrahedral shape because it's 1 atom bonded to 4 different, so that would have a bond angle of 109.5. That's the tetrahedral, and it's bonded to 4 different shapes. So now looking at enantiomers. So enantiomers are basically the same as optical isomers, and it's just a different word for optical isomers. We just tend to use enantiomers. And enantiomers are, so the definition which you can be asked in an exam is that enantiomers are molecules which are non-superimposable mirror images of each other. So just learn this definition really well. So molecules which are non-superimposable mirror images of each other. So looking at these enantiomers as an example, so I can see that these are tetrahedral, and the chiral center is bonded to 4 different groups. So this must be an enantiomer. So as I can see that there is a mirror line in between, and these are basically reflections of each other. So looking at the top, we have pink at the top, pink in there as well, blue on the far end from the reflection line, and blue is on the far end of the reflection line in this as well, green there, and the yellow is there. So I can see that this is a mirror image of each other. So this fits in with the definition mirror images of each other. Now, what is meant by that non-superimposable? So what this means is, if I, for example, if I get this first molecule, can I get the first molecule to look exactly the same as the second molecule? or can I get the second molecule to look exactly the same as the first molecule? So having that first molecule, as you can see, this looks exactly the same. So can I make the second molecule look exactly in the same way as the first molecule? And if we can do that, then the molecule will be superimposable. Now, if we try and do that, we can try and do that as many times as we like, trying to make both molecules look the same, but we'll never actually be able to do that. There will be a difference in the two molecules. That's why these are called non-superimposable mirror images of each other. So even though there are mirror images of each other, they will never be able to look exactly the same. If we were to place them right next to each other, they would look different. So an example could be just looking at your hands. So you can say that your hands are non-superimposable mirror images of each other. So if, for example, if I put my right hand there, left hand there, so they, if I look at them comparing each other, they're basically mirror images of each other. But if I were to make my hands look exactly the same like this, I would never actually be able to do that. You can try and do that with your own hand, and this is why your hand is basically non-superimposable mirror images of each other, your two hands, and that's the same with these enantiomers. Now you need to be able to know how to draw enantiomers. So for example, if we are given this this molecule, I know that this can form an enantiomer because this has a carbon which is bonded to 4 different groups. So when I'm asked to draw an enantiomer of this, what I do is I draw a mirror line in between. So mirror line to show that there will be mirror images of each other. So what I then do is I would draw the carbon first, and then I would draw the molecule which will be the closest. So for example, COOH, I think it's close, so I would draw this first. So I can say this would be C, and because we are because OOH is moving towards the mirror line, I'm going to draw it like this. So it'd be CCOH. And next I can draw the hydrogen, so that would be towards this side, so I will have my hydrogen there, and drawing my oxygen, so this will be there, and then I can finish off by drawing the CH3. So this would be my mirror image, and this would be my two enantiomers. So just as a note, that it does not matter where you place the different molecules when you're drawing from the start. So for example, I could have had my H there, I could have had my OH there, so it does not matter, you can place them anywhere. If I have drawn my first molecule like this, my second molecule should be an exact mirror image of each other. So if I have drawn my COOH group there, then the COOH group can't go there, there or there. It has to go in that position. And also what some people mistakenly end up doing is so for the CH3 bond, for example, they might end up drawing H3C. Make sure that the bond which the carbon or the chiral center is bonded to comes first, so it should be CH3, not H3C, and it's the same with, for example, COOH. It should not be HOOC, so keep that in mind. So the enantiomers have the same physical and chemical properties. Now, because even though they are slightly different in their spatial arrangements, they have the same electron structure and the same arrangement of electrons, so that's why they have the same chemical properties. And because they don't really differ in any of their groups in anything really, and they have the same physical property because they have obviously the same bonding and everything else. But what they differ in, and you need to know this to differentiate between the two different enantiomers, is their effect on plane polarized light. So what we do is, to differentiate them, what we can do is we can shine plane polarized light through the sample So for example, I would shine the plane polarized light through there, and what happens is the enantiomers, so the different enantiomers would rotate the light equally, but they would rotate the light in opposite directions. Now this is what would help me differentiate between the two enantiomers. So for example, a normal light, it would move in all directions, so it's not restricted to move in any direction. But when enantiomers come, for example, this enantiomers make the light rotate in anti-clockwise direction, whereas the other enantiomer would make it rotate in clockwise direction, and this could help me differentiate between the two enantiomers. And also their reactions with other chiral molecules can help me differentiate between the two enantiomers. So you need to be aware of RACEMIC mixtures. So the RACEMIC mixture, what they are basically, they are just a 50-50 mixture of the two enantiomers. So they have equal amounts of the two different enantiomers. And they would not be optically active, so they would not rotate the light in a clockwise or anti-clockwise direction. This is because both of these enantiomers rotate plane polarized light equally, but they will rotate it in opposite directions. And what this causes is the rotations from the enantiomers to cancel out, because looking at this example, the first enantiomer is moving the light in plane polarized light in anti-clockwise direction, whereas the other one is moving it in clockwise direction. So if we were to add them up, they would just cancel each other out, so we would just get this this straight line instead of having those rotations. Alright, so you need to be aware of how RACEMIC mixtures are formed. So to do this, we have to look at the structure which comes before the tetrahedral structure. So for example, we have, and in this example we have butanons. So if I were to look at the 3D shape of this molecule, I can see that the double bond is there, one bond's there, one bond's there. So there's basically 3 different bonds, and that's why it will have a trigonal planar structure. So this means that there's no bonds sticking out of this. So this is the double bond, so this will be the double bond in there. So so for example, if the double bond is being attacked by a nucleophile, so an electron pair donor, so if we have, for example, a hydride ion, so that's a nucleophile. So what happens is, because we have access to that double bond from either side, it can be attacked from this side or that side. So for example, the hydride ion can attack the double bond from this side, from the left side, and it can attack the double bond from the right side. What this means is that there is an equal chance of attack on the planar carbonyl group from either side, and this forms a 50-50 mix of the enantiomer, because the hydrogen bond which will be formed when the attack's complete can form from either the left side and the right side, and because the hydride ions have access to that bond from both of these sides, there is an equal chance of the enantiomer being formed. So the pink being that the hydrogen bond, so as you can see, if we attack from the left side, this would form, and if we attack from the right side, this would form. So because there's an equal chance of the enantiomers, the 2 different enantiomers forming, we end up getting a 50-50 mix of these enantiomers, and that's how a RACEMIC mixture is formed. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.